Radiation, or radioactivity, is one of the scariest words in the English language. While radiation can indeed be very dangerous, most people don't really understand how it works, and it's often treated as magical death cooties, which leads to unwarranted fear. Learn more about radiation, how it works, and where it's found in nature on this episode of Everything Everywhere Daily. This episode is brought to you by the Travel Photography Academy. Have you ever been on a trip and wondered why your photos don't turn out like the images you see in travel magazines? If you're going to spend thousands of dollars on a trip and hundreds to thousands of dollars on a camera, you owe it to yourself to get the highest quality images from your trip. That's why I created the Travel Photography Academy. I set out to travel around the world in 2007 with an expensive camera, and I had no idea how to use it. As I traveled around the world, I taught myself the art of travel photography, eventually mastering it to a point where I was named Travel Photographer of the Year 3 times in North America. The Travel Photography Academy is an online course that teaches you everything you need to know to master your camera and to take better photos on your next trip. To improve your photography and to get better images on your next trip, visit travelphotographyacademy.com or click in the link in the show notes. We need to start any discussion of radiation with what it is. The textbook definition of radiation says that, quote, radiation is the emission or transmission of energy in the forms of waves or particles through space or through a material medium, unquote. This actually includes a large number of things, including light, radiant heat, and radio waves. However, when we hear people talk about radiation, they're usually not talking about light bulbs and radio antennas. That's because there are two different types of radiation: ionizing and non-ionizing radiation. Visible light, radio waves, and the things we deal with on a daily basis are all non-ionizing radiation. The stuff that deals with nuclear power, bombs, or medical procedures is all classified under ionizing radiation. Ionizing radiation just means that the energy emitted in the particle or photon is high enough to remove an electron on an atom or break a molecular bond. For the rest of the show, when I refer to radiation, I'll be referring to ionizing radiation, because that's really the focus of the episode. Ionizing radiation comes in 3 forms: alpha particles, beta particles, and gamma rays. All 3 of these types of radiation are due to a process called radioactive decay. So if you remember back to your science class, all atomic nuclei are made up of protons and neutrons. Protons have a positive charge and neutrons have a neutral charge. The number of protons determines what the element is. For example, iron will always have 26 protons. If it had anything else, it wouldn't be iron. However, iron or any other element can have different numbers of neutrons. 92% of all iron in nature has 30 neutrons. There are also some that have 28, 29, 31, or 32. All of these different numbers are called isotopes. And in the case of iron, there are 5 isotopes that make up over 99.9% of all the iron you can find. These isotopes are stable isotopes. A stable isotope, just as the name implies, means that it's happy just as it is. However, some isotopes of some elements are unstable. That means they can only stay in that state for so long, and eventually it's going to change. When they change, that's called radioactive decay. It's important to know the difference between the 3 types of decay: alpha, beta, and gamma. Alpha decay is when a nucleus spits out a helium atom. 2 protons and 2 neutrons will be expelled from the atom, turning the atom into a new element. All of the helium we have on Earth comes from the process of alpha decay. Radioactive elements deep in the Earth undergo alpha decay, spit out a helium atom, and the helium gets trapped under the Earth. Helium on the surface will quickly go to the top of the atmosphere and disappear. Of the 3 different types, alpha radiation has the lowest energy and can be the safest type of radiation. An alpha particle can be blocked by almost anything. A piece of paper, your clothes, or even your dead skin cells will block an alpha particle. The danger in alpha particles comes from if you should ingest them. If an alpha emitter were to get into your lungs, it could cause a great deal of damage. That is why radon can be so dangerous. You might remember a Russian critic by the name of Alexander Litvinenko who was poisoned with polonium-210 back in 2006. Polonium is a very radioactive alpha emitter with an extremely short half-life. Litvinenko was poisoned with it and died, and he's believed to be the first victim of polonium-210 poisoning. The second type of radioactive decay is beta decay. This happens when a neutron spits out an electron or a proton spits out a positron. Beta particles have more energy than alpha particles. A piece of paper or some clothing isn't going to stop beta radiation. You'll need something like a thin metal sheet to stop it. A beta particle is about 100 times as penetrating as an alpha particle. Strontium-90 is a common beta emitter, and it's often used for medical purposes. Doctors will target beta emission on a tumor to attempt to kill it. The final type of radiation is gamma radiation, and this stuff is really nasty. Unlike alpha or beta radiation, which is a physical particle ejected from an atom, gamma radiation is a high-energy photon. Because it's a photon and has no mass, and because it has so much energy, blocking gamma rays is quite difficult. It requires thick layers of concrete or lead shielding. If you're ever required to swallow something in a medical procedure so they can track it through your body, it'll probably be a very weak gamma emitter, just because the rays are likely to travel right through you. Of the three types of radiation, alpha emitters are the safest to have outside your body and the worst to have inside your body. Likewise, gamma and beta emitters are the safest to have inside your body and the most dangerous to have outside your body. What most people don't realize is that they're exposed to radiation every second of their lives. In fact, you, listening to this podcast right now, are yourself radioactive. Natural radiation comes from two primary sources. The first is cosmic rays. Cosmic rays are high-energy particles that come from space. They might have come from the sun, or they may have come from another galaxy. They're just whizzing around all the time, entering our atmosphere. So, unless you're listening to this in a really deep mine, you are being bombarded by cosmic rays. Moreover, the higher up you are in altitude, the more cosmic rays you're exposed to. Someone living in Denver will get as much background radiation due to the altitude as someone living in Chernobyl. And that's really more of a statement of how low the levels are in Chernobyl than how high they are in Denver. Likewise, flying is one of the things which is responsible for the largest exposure to radiation which most people will receive. A single transatlantic flight will give you more radiation exposure than 5 chest x-rays. If you look at the list of jobs with the highest exposure to radiation, you'll see an airline pilot right next to a nuclear medical technician. The other major source of natural radiation is background radiation from the Earth. Elements like uranium are natural and found in rocks and in the soil, often in trace amounts. Usually unstable isotopes like carbon-14 are also produced in the upper atmosphere by cosmic rays. Living in a house made of stone, as opposed to one made of wood, will increase the amount of radiation you're exposed to. Likewise, as odd as it may seem, a coal-fired electrical plant will cause more radiation exposure than a nuclear power plant. The reason is that there can be trace amounts of naturally occurring radioactive material in coal, which when burned will travel in the atmosphere and be inhaled into people's lungs. Everything in a nuclear power plant, however, is shielded and never exposed to the outside. This natural radioactive decay is also what's responsible for most of the heat in the interior of the Earth. Geothermal energy is really just nuclear power using the Earth's mantle and core as the reactor. So how is it that you, podcast listener, are radioactive? This mostly comes from potassium-40, a naturally occurring isotope that makes up 0.012% of all potassium. Because you have potassium in your body, some small amount of that will be radioactive, and hence, you are. One of the most radioactive foods you can eat is a banana, because it has so much potassium. All of the things I've mentioned are true, but they're very low levels of radiation. As I mentioned before, ionizing radiation can destroy molecular bonds, like in our cells or in our DNA. However, life evolved on the planet in such an environment, so our bodies can repair a certain amount of cellular and DNA damage. When it gets too much, that's when we run into problems. How radioactive something is can be measured in terms of half-life. Half-life is a pretty easy concept. Because radioactive decay involves an atom changing into something else, the half-life is just the length of time it takes for a unit to become half that amount. So if you have a gram of uranium-238, the half-life would be the amount of time it takes until you only have half a gram left. In the case of uranium-238, that would take 4.5 billion years. The thing with half-lives is that the shorter the half-life, the more dangerous it is. In the example I gave above of polonium-210, it has a half-life of 138 days. It's extremely radioactive. Uranium-238, you can easily hold it in your hand. So, what's the deal with nuclear power and nuclear bombs? Those could be entire episodes on their own, and perhaps they will someday. But I'll oversimplify it and just talk about the things which most bombs and reactors have in common. Uranium-235. Natural uranium comes in two forms. Uranium-238, which makes up 99.3% of all the uranium, and uranium-235, which makes up the other 0.7%. To make a nuclear reactor, you need uranium-235, the rare type, which has a half-life of about 700 million years. The problem is, you need to separate it from the uranium-238, which is really hard to do. Separating two different elements is pretty easy. You can do that chemically. Separating two different isotopes is really hard to do because they're basically the exact same thing except for a small difference in weight. When U-235 is hit with a neutron, the atom splits and sends out more neutrons, which split more atoms and send out more neutrons, etc., etc. If you have a whole lot of U-235, then you get an uncontrolled reaction, and that's how you make an atomic bomb. You would need over 90 to 95% U-235 to create weapons-grade uranium. That is very hard and very expensive to do. To make fuel for a nuclear reactor, you want U-235, but not so much. The fuel in a nuclear reactor only has 3 to 5% U-235. That's why a nuclear reactor literally cannot blow up like an atomic bomb. If a half-life means that there's less of something over time, that means in the past there must have been more of it. Because of the different half-lives of U-238 and U-235, is it possible that in the deep past of the Earth, there was enough U-235 to cause a natural nuclear reaction? The answer, believe it or not, is yes. They found evidence in the nation of Gabon that 2 billion years ago, a natural nuclear fission reaction had to have existed given the isotopes they now find there. It would have created a lot of heat not too dissimilar from a volcano. You might have heard of something called plutonium. Plutonium is not a naturally occurring element. It's only found as a byproduct of man-made nuclear reactions. It is really nasty stuff and one of the deadliest substances on the planet. However, it has its uses. The primary use for plutonium is as a fuel for deep space missions. Whenever we send a probe to Jupiter or beyond, it will always be fueled by plutonium-238. Solar panels just don't work when you're that far away from the sun, so you need something else. Plutonium-238 has a half-life of 88 years, so it's pretty radioactive. It produces a lot of heat, however. A block of it could sit in one place and be hot for years and years, which is perfect for powering a spacecraft. For example, on the New Horizons mission to Pluto, it was powered by a radioisotope thermoelectric generator, or an RTG. This takes the heat from the plutonium and converts it directly into electricity. It's a very safe and simple power source for deep space, but it isn't very efficient. Only 3 to 7% of the heat is converted to electricity. But when you're billions of miles away and you have years to get there, you have plenty of time to charge up your batteries. If you've ever wondered how we can still keep in touch with the Voyager spacecraft 43 years after they were launched, it's due to plutonium-238. Not long ago, NASA was worried about the supply of plutonium-238 because they were running out of it and couldn't fuel deep space probes. Since then, they've discovered a new way to manufacture it, so we have plenty for the future. Radiation is something that definitely needs to be respected. It can do a great deal of damage. However, it's also something that is natural, and at certain levels we've lived with every day of our lives. So the next time you hear something about radiation on the news, instead of thinking of it as magical death cooties, take a more nuanced approach. Compare it to the background radiation you receive every day, or the amount you might receive on a plane flight, to get a better appreciation for what's really happening. Executive producer of Everything Everywhere Daily is James Makkyla. The associate producer is Thor Thomsen. Remember to leave a 5-star review to get your review read on the show. They can be left at Apple Podcasts, Podcast Republic, or wherever you listen to the show. Also, you can help support the show over at patreon.com. Patrons can get merchandise like t-shirts and hoodies, as well as having direct access to provide suggestions for future episodes.